2011 BMO1 question 6. Let ABC be an acute angle triangle. The feet of the altitudes from A, B, and C are D, E, and F respectively. Prove that DE plus DF is less than or equal to BC and determine the triangles for which equality holds. So, first we should draw in the lines DE and DF. Now, this configuration is simply the orthocenter configuration, and we'll mark the orthocenter with H. So, this is actually a very nice problem, and it doesn't involve that complicated steps, but it's quite hard to figure out. And the reason it's hard to figure out is because there's so many things one could try. And because this is question 6, maybe people might try power of a point, which might work. People might try extensive angle chasing or trigonometry or things like that. And they work, but the solution I'm going to show you today is my favorite solution. And of course, it boils down to cyclic quadrilaterals. So, first of all, angle BFC equals to angle BEC. So by angles in the same segment, BFEC is cyclic. Now I've already drawn in this circle, like that. So that's a circle. What else do we know? Now BC is the diameter, because by Thales, a right angle triangle has the hypotenuse as the diameter of its circumcircle. So I'm just going to write that down. This is the diameter. Now, what else do we know? Okay, so if we're trying to find the other cyclic quadrilaterals, then by a similar logic, ABDE is cyclic, and also AFDC. You can try and work out for yourself why this is true. Hint, it's the same as before. But we're going to be focusing on this cyclic quadrilateral because it states that we have to find something concerning with BC. And we know BC is the diameter, so that's a good start. Now, here's the key step. Reflect F in BC. So, take the point F and reflect it in the line BC. Now, since BC is the diameter, F dash also lies on the circle. We can join F dash to D. Now, what we want to prove is that FDE is a chord. Because if we can do that, then we can prove that a chord is at most the length of the diameter, so this is true. So to prove that it's a chord, we have to try and prove that it's collinear. And to prove that it's collinear, we're trying to prove that angle BDF dashed equals to angle EDC. And this is actually quite simple. Because we're reflecting, angle BDF or BDF dashed equals to angle BDF And this is equal to 180 minus angle FDC. But if we remember that AFDC is cyclic, then 100 minus AFDC is angle A. And this also equals to 180 minus angle BDE, remember? So I'm going to write here reflection. It's always a good idea to write down your reasoning. Angles on a line, cyclic, and this equals the angle EDC. So all of these angles are the same, which means we proved this. It's actually an interesting tool to use if you want, that the external angle of a cyclic quadrilateral is the same as the opposite internal angle. So actually I'll mark them with this pink thing. And also this. The opposite external angle of a cyclic quadrilateral is equal to the opposite internal angle, like this. Again, you can try and prove this if you want. So, what have we proved? We've proved that BDF and EDC are both the same, and so F-DE is a line. And it's a chord of circle BFEC. Now, the only way that the chord is equal to the diameter is if D is the midpoint of BC. So a chord is at most the diameter, so BD or FD plus DE equals to F-D plus DE, which is equal to F-E, which is a chord, and it's less than or equal to the diameter BC, so that's the diameter. We've proved this. Now, to find the cases where it's equality, where equality holds, is when D is the midpoint of BC. If D is the midpoint of BC, then that means that it's an isosceles triangle. So this is the whole question. It's actually not that hard. It doesn't require that much knowledge. It's just the basic circle theorems, but applied in a very, very beautiful way, especially this reflection, which I will actually highlight in green. This is the key step. Please subscribe. Thank you for watching. Bye.